Welcome to Math TV with Professor V. This is video lecture for section 2.1, operations with matrices for linear algebra. So it's standard mathematical convention to represent matrices in any of the three ways listed below. First option is you can just use an uppercase letter like A, B, or C. Another option, too, is a representative element enclosed in brackets. So you would have like lowercase a sub ij, so that would represent matrix A, or lowercase b with subscripts ij, because that's a representative element that belongs in the matrix, so that would represent matrix B, or C sub ij, etc. And then another option is a rectangular array of numbers. So you have the elements listed with their subscripts and then ... to fill in, since this matrix here is with m rows and n columns. So we leave it arbitrary size. So again, this is the same as if we had written A sub ij or just A. Okay. So some definitions, we say that two matrices, A and B, are equal when they have the same size, m by n. And A sub ij is equal to B sub ij for I between 1 and m, those are all the rows, and j between 1 and m. So basically, matrices are equal when they have the same size and all the corresponding entries are equal to each other. Okay, and if you have two matrices and they're both size m by n, so they're the same size, but they don't have to be the same matrix anymore, then the way you find their sum is you add all of the corresponding entries in each place. So their sum is going to be the same size, and to find each of the new entries in the sum, you just add the entries that are in each of the matrices. Okay. The sum of two matrices of different sizes is undefined. So basically they can't be added together. They have to be the same size. If you have another matrix A and it's an m by n matrix and C is a scalar, so just some number, a constant, then a scalar multiple of A by C is the m by n matrix written C, you put the scalar in front, and then you have capital A for the matrix, and you basically just multiply every single entry in the matrix by that constant C. Okay? Now, what if you want to take a matrix and multiply it by another matrix? Do they have to be the same size? Not necessarily. So, if you have two matrices, A, which is an m by n matrix, and then B, which is an n by p matrix, then the product AB has size m by p, okay? And this is the formula for how to find the product of these two matrices, but don't write it down or memorize it. Honestly, I'll just show you a way for you to understand kind of how it works. But here's how you check if you can even multiply two matrices by each other. So we have matrix A, and here in this definition it tells us it's size m by n, right? And you want to know, okay, can I multiply it by matrix B? Is this going to be allowed? And matrix B is size n by p. So yes, the size here, the number of columns of A must match the number of rows in matrix B. So that works out. Since those are matchy-matchy, we are allowed to multiply them. And then the size of the product, after you multiply them, the result is going to be an m by p matrix. That's the size of the product, AB. M rows, p columns. Okay? Good. If these entries, so if the number of columns in A is not the same as the number of rows in B, then you can't find the product. Just go, I can't do it, not possible. All right, so let's look at an example. I told you not to memorize this little summation formula. I'll show you how it works just by examples. So here we have matrix A, matrix B, and then find the following products if possible. All right, so let's check first if we can even do this. Matrix A is what size? A has 2 rows and 3 columns. And matrix B has 3 rows and 2 columns. So can we multiply these matrices? Yes, because notice these entries are the same. Columns in A is the same as rows in B. I just think the two, those two numbers next to each other have to be the same. And then the product is going to be a 2 by 2 matrix. 2 rows, 2 columns. Okay, so the product, it's possible, it's going to be a 2 by 2. All right, so here's what you do. We're finding A times B, so I'm going to list A first on the left, 4, -5, -3, 2, 1, 0. Now matrix B, 2, 0, -4, 1, -3, 7. I'm going to go super slow for the first time, and then later on, you'll get good at doing them in your head. Okay. Always take the second matrix, grab a column working from left to right. And here's what I always tell my class. Take a column to make a column. Okay, so I took this first column here, 2, 0, -4. I'm going to list it up top, 2, 0, -4. And I'm going to use that to make the first column in the new matrix, the product. How do I do it? You multiply the corresponding entries here. So you take 2 times 4, so that's going to be 8. Plus, just keep adding these corresponding products here. 0 times -3, so that's 0. Plus this product here, -4 times 1. That's the first entry. This right here is my new A11, or C11, because it's the product, right? Let's call it C11. Okay, take a column to make a column. So what does that mean? Now I'm going to move down, take 2, still take that first column from B, times -5. Okay, that's -10. Plus, keep going, 0 times 2, that's 0. Plus, -4 times 0, that's 0. Okay, so now I've made my first column. Repeat the process. Now I'm going to come along, grab the second column in B. I'm going to write it up top here. So let's erase these guys. Okay. 1, -3, 7. And I'm going to make my second column. Take a column, make a column. Okay. So 1 times 4, that's 4. Plus, then we've got -3 times -3, that's going to be 9. Plus, keep it going, 7 times 1, that's 7. All right, then move on, take these products, boop, 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 add them together. That's going to give us second row, second column entry. So 1 times -5, -5, plus -6, plus 0. Okay, that's it. I know it seems tedious at first, but once you get the hang of it, you're going to do a lot of this in your head. You won't be writing out all of this. Honestly, you're just going to do it mentally, and it's going to be fabulous. Okay, so cleaning things up now, we've got a 2 by 2 matrix. 8 plus 0 plus -4, that's 4. This is -10. We have here 13 plus 7, so 20, and then -11. This is the result. This is A times B. Wonderful. Look at us go. Okay. It's just going to take practice, and you'll eventually start doing these on autopilot. Okay, let's try another one. This time it's B times A. So we found the product AB. Now they're asking us to do BA. Can we even do it? So let's see. B, remember, B was size 3 by 2. And A is a 2 by 3. So yeah, we can take this product because those values match up. Columns in B matches rows in A. And the size of their product is going to be a 3 by 3. Ooh, okay. So 3 rows, 3 columns this time. So since we're finding B times A, yes, I want you to write matrix B first. So 2, 0, -4, 1, -3, 7. And then here's matrix A, 4, negative 5, negative 3, 2, 1, 0, like that. And the result is going to be a 3 by 3. All right, so remember, take a column to make a column. So take this first column, always working left to right. I'm going to write it up top here, 4, negative 5, and we're going to make our first column. So you go 4 times 2, that's 8, plus negative 5 times 1, so that's negative 5. Okay, moving down. See how that was the top left entry? Now I'm going to move down, take these products, and that's going to make the entry beneath it. So it just fills in a corresponding fashion. We're going to have 0 plus 15. Yes? Good. Keep going. That's going to make this one. 4 times negative 4, that's negative 16. And then negative 5 times 7, negative 35. Okay, why don't you pause the video, try to do the others, and then check if you did them correctly. You should make 2 more columns. Okay, so here we go. I'm just going to fill in quickly the rest. So up top, you should have negative 3, 2. And this is going to be negative 6 plus 2, 0 minus 6, and then 12 plus 14. That one's done. And then last column is going to be 1, 0. Let me switch colors. 1, 0. I always like when I have a 0 because you can just ignore all the products from that guy, right? And when you have a 1 times something, it's just going to copy that column in here if you hadn't noticed. So 1 times 2 is 2, and then 0 is not going to do anything. 1 times 0, 0, and then 1 times negative 4, negative 4. Okay, so adding everything together, cleaning up, we're going to have 3, 15, negative 51, negative 4, negative 6, 26, 2, 0, negative 4. Beautiful. Okay, let's box that and make a very important observation at this point, and that is that matrix multiplication is not commutative. Notice we saw, just based on this example, that the product AB is not equal to BA. So you're going to have to be very careful. Keep that in mind. AB, remember, it was a 2 by 2 matrix. BA was a 3 by 3, so already the size isn't even the same. And matrix multiplication is not commutative. That's the big takeaway here. Okay, previously we were talking about systems of linear equations. So now we want to kind of make a little bit of transition, since we're so professional at multiplying matrices, and how we can represent our systems of linear equations using a matrix and multiplication. So observe that the following system of equations can be written in the following form. So you can have here first the coefficient matrix, and then all of the variables. Notice we had n unknowns, so we label them x1, x2, all the way up to xn. So all of these variables, this column matrix, we actually can represent as a vector x, and you put this little symbol up top to show that it's a vector, okay? And then this is equal to all of the constants here that were on the right-hand side. Again, that's a column vector, which you can also represent with the notation B with the little arrow on top. So when you see this, you know, oh, it's a column vector quantity, so you've got all these entries, okay, that make up B. And we say that this whole equation can be just simply summarized as AX equals B. So again, A is our coefficient matrix, and then X and B are column matrices, okay? So to see exactly how it works, we're going to look at an example, and then we're just going to end up doing row operations in the end, okay? But just for you to see the setup. So the directions look different than what you've seen before, but the process and how we're going to solve is the same, nothing new, just switching up the way we ask questions. So here it says solve the matrix equation AX equals B, okay? And here's the thing to remember. So the coefficient matrix A has size m by n, and you're multiplying it by column matrix X, right? And X has n rows and 1 column. And the result is column vector B, which is going to be size m by 1. Okay, so it all checks out. So here we're going to solve this matrix equation AX equals B. Let's see, the size of A, it's 2 by 3. The size of X, that should be bold or have a vector on top. X is 3 by 1, and B is 2 by 1. Is this possible? Does this check out? Well, let's see. These are the same. Columns of A matches rows of X. These are the same. So yes, we are allowed to multiply A and X. And the result is going to be a 2 by 1, which is precisely the size of column vector B. Okay, so everything's good. AX equals B checks out. And what would the result be? Well, you can just look back. We're going to have the following system of equations. Remember, this is the coefficient matrix, and we have our 3 variables, x1, x2, x3. So we would have 2x1 minus x2 minus x3 equals this entry here, which is just 0, and x1 minus 2x2 plus 2x3 equals 0. Homogeneous system of equations. So you can, solve it now however you want. Let's just use our row operations and represent everything with the matrix so we don't have to write x1, x2, x3, because that's no fun. So let's write out our good old augmented matrix and do some Gauss-Jordan elimination, right? Okay, so you can already tell we only have 2 equations and 3 variables, so we're not going to have a unique solution. Nope. And let's see if we remember how to do this, guys. You want a 1 in the top left entry. You got to make your pivot. So you could divide everything by 2. I'm not going to do that because I don't want these to be halves. I'm not anti-fractions, but I definitely try to avoid them when possible just because they complicate things. So how about we just switch row 1 and row 2? Because, oh, there's a 1 sitting right there. That sounds nice. That sounds less troublesome. So to get to the next step, we're going to interchange row 1 and row 2. Always write what you're doing, okay? It's for you, it's for your instructor, it's for everyone's well-being, honestly. Okay, we've got 1, -2, 2, 0, 2, -1, -1, 0. Great, that was painless. Now we've got a 1. Top left, we've got our pivot. What do we do with the pivot? We use it to 0 out everybody else in that column. So this needs to be a 0. Okay, hopefully by now you can identify what we need to do. So you're going to take -2 times row 1, add it to row 2, and that's our new row 2. Notice I write the new row with the capital R. So we're only replacing row 2. Let's rewrite row 1 as is. Okay, so you don't get tempted to do something wild. And then, yeah, let's do this in our head. We've grown, we can handle it. So -2 times 1 plus 2 is 0. That was the whole point of this. And then -2 times -2, that's +4, minus 1, that's 3. Look at us go. And then here we've got -2 times 2, that's -4, minus 1, -5. And then it's fabulous over here. Just whatever you do to 0, add it to 0, it's still 0. Great. Okay, next we need to make our pivot in column 2, which is right here, so that 3 needs to be a 1. I'm so sorry, there's nothing to do besides divide by 3 this time, so we'll suck it up and introduce some fractions. It's okay. So 1/3 times row 2 is my new row 2. Notice again, nothing's happening to row 1. So let's rewrite it first. just because sometimes students are doing wild things to the rows that aren't supposed to change. It can get overwhelming if you're not focused. Okay, so my new row 2 is going to be 0, 1, -5/3, and 0. Great. So now that we have our pivot all handled, remember, I use it to zero out everybody else in the column. So this -2 needs to become a 0. How shall we do that? Well, let's take 2 times row 2, add it to row 1, and that's my new row 1, right? Okay, so in this case now, row 2 is not changing. So I'm going to rewrite 0, 1, -5/3, 0. And then we're going to fill in now. So this is going to stay a 1. This becomes a 0. Now just think. 2 times -5/3 is -10/3 plus 6/3 is -4/3. Okay. And then this is still 0. Okay. That's as good as it's going to get, right? So we are in reduced row echelon form. Let's just rewrite now what the system of equations would be that corresponds with this matrix now. So we've got x1 minus 4/3 x3 equals 0. Solving for the variable that's furthest on the left always, we've got x1 equals 4/3 x3. And then the second equation is x2 minus 5/3 x3 equals 0. I'm going to solve for x2. It's furthest on the left. And we get 5/3 x3. So we've got one free variable, x3. I can write my solution, the ordered triple, x1, x2, x3, all in terms of x3, right? Did you notice that? So x1 is 4/3 x3. Then we have 5/3 x3, and then x3. And I know I've shown you guys this in the past. You can factor out the x3. So you'd have 4/3, 5/3, 1, all multiplied by x3. So a few different ways you can write your answer, okay? Be familiar with them all. They're all useful in different contexts. So, you know, you don't want to be a one-trick pony. And then in some books, instead of x3, they'll replace it with another variable, usually t or something of that sort. Okay, so then you could write your solution as 4/3 t, 5/3 t, t, and of course t could be any real number. Okay, so just check with your instructor, look at your textbook, be adaptable, but it all means the same thing. Okay, now we're going to shift gears a little bit and talk about linear combinations of column vectors. So the matrix product AX is a linear combination of the column vectors A1, A2, up until AN, and these should either be bold or have the little vector symbol above them, so you know they're column vectors. And they form the coefficient matrix A. So just to revisit that coefficient matrix over here, this is our coefficient matrix A, but each column we can regard as a column vector if we break it up. So this first column, you could look at it as column vector A1. Second column is column vector A2 up to AN. So that's basically what we're doing right here, okay? So here's A1, A2, AN, and we're multiplying each column vector by x1, x2, up until xn. And furthermore, the system AX equals B is consistent if and only if B can be expressed as such a linear combination. So we'll talk about that more later in the course, but for now, I just want you guys to understand that we have another way to represent our system of equations here, okay, using linear combinations of column vectors. So if we just revisit the last example that we worked on, the system of equations AX, matrix A was 2, 1, -1, -2, -1, 2. And then X, that column vector was x1, x2, x3, right? Equals 0, 0. So all I basically want you to get out of this is that this is the same as writing each column as a column vector now, 2, 1, and then you would multiply by x1 plus, move to the next column, negative 1, negative 2 times x2, and then one more. In this case, n is 3, negative 1, 2 times x3 equals 0, 0. Okay, so that's just another way to represent your system of equations. What makes this a linear combination? You have products and addition. Product, addition. Okay, so that's it. Just a different way to represent a system of equations. Keep that in mind. We'll revisit this more later in the course with more detail. Okay, kind of shifting gears back to what we were doing, just way more spicy. So write the system of linear equations in the form ax equals b, and then solve the matrix equation for x. Holy moly, we've got 4 equations, 4 variables. So let's do this. They want us to solve it in the form ax equals b. So you would have coefficient matrix A, 2, 0, 1, 1, negative 1, 3, 0, 1, 0, negative 1, 1, 2, 1, negative 1, negative 3, 0, times x. So that would be x1, x2, x3, x4. We've got 4 variables, equals b, 3, negative 3, negative 4, 0. Okay, that's what we're solving. Okay, Gauss-Jordan elimination time. So I know I want a 1 in the top left, and I'm not going to divide by 2 in that first row because I've got some options. I can switch things around, can't I? So here you're going to ask yourself, do I want to move row 4 to row 1 or row 3 to row 1? And I'm going to move row 3. Why? Because I notice there's already a 0 here, which is also going to be a goal down the road. So let me just move that guy up there. It'll make life a lot nicer. I'm thinking ahead. I'm looking out long term. Okay. So here we go. I'm going to write the augmented matrix first. 2, 0, 1, 1. Negative 1, 3, 0, 1, 0, negative 1, 1, 2, 1, negative 1, negative 3, 0, and 3, negative 3, negative 4, 0. Okay, so first thing we decided we were going to interchange row 3 and row 1. Too long. I want to make sure this problem will fit here. Let's see. So now row 1 is 1, 0, 1, negative 3, negative 4, and then we've got everything else. 0, 3, negative 1, negative 1, negative 3, 2, negative 1, 0, 1, 3, 1, 1, 2, 0, 0. Boop, boop, beat it. Okay. Oh, look, we already have a 0 here. Now my task is use the pivot, use the 1 to 0 out everybody else in the column. So this needs to be a 0, this needs to be a 0. We can handle doing both at the same time. If you're in linear algebra, you're an advanced math student, so pull it together. We've got, how do we make that 2 a 0? You take negative 2 times row 1, add it to row 3, that's your new row 3. And then the 1 at the bottom is going to be a 0. You take a negative times row 1, add it to row 4. That's your new row 4. Which rows are not changing? Row 1 and row 2. So kindly rewrite them first now. That way you're not tempted to do something wacky. So 1, 0, 1, negative 3, negative 4. That's staying the same. 0, 3, negative 1, negative 1, negative 3. That's staying the same. New row 3. Here we go. This is going to be a 0. And then negative 2 times 0 minus 1, that stays the same. Negative 2 plus 0, negative 2. 6 plus 1, 7. and 8 plus 3, 11. You should be able to do this mentally by now. Okay, last row, 4, that's a 0. That's a 1. Ooh. And then that's going to be a 1. Positive 3 plus 0, 3. And positive 4 plus 0 is 4. Okay. Here you go. Moving our attention now to this little sucker who needs to be a 1. Okay, we need to make our new pivot. Do I want to divide by 3? Not really. I see a lovely positive 1 sitting right here in row 4. So let's just swap row 2 and row 4. You don't want to swap row 1 with anything at this point. Leave it where it is because you've already made the pivot. So don't touch it. No swapping that row. But, you know, row 4, no problem there. So let's interchange row 2 and row 4. I love it. So row 1's not changing. 1, 0, 1, negative 3, negative 4. Row 2 is now, let me do it in a different color. 0, 1, 1, 3, 4. Row 3 is not changing. 0, negative 1, negative 2, 7, 11. And then now row 4 is 0, 3, negative 1, negative 1, negative 3. Great. You could always, you know, divide by 3. Everything will still turn out the same in the end. You're just going to have fractions in all your row operations so much sooner, and it makes life more difficult. More probability that you're going to screw up somewhere. We don't want that. Okay, now we have our pivot. So lovely. Let's zero out everybody else in that column. So this negative 1 needs to be a 0, and this 3 needs to be a 0. How do we do that? The negative 1's going to be easy squeezy. You just take row 2 plus row 3. That's your new row 3. And then negative 3 times row 2 plus row 4 is my new row 4. So rows 1 and 2 are not changing. Okay, so we've got 1, 0, 1, negative 3, negative 4, 0, 1, 1, 3, 4. That's not changing. And then now let's see, my new row 3, I'm going to take row 2 plus row 3. That's, oh, I wanted it light blue. Okay, 0, 0. Row 2 plus row 3 is my new row 3. This is negative 1. 3 plus 7, that's 10, and 4 plus 11 is 15. Negative 3 times row 2, okay, so this stays 0. This is now 0. Negative 3 minus 1, that's negative 4. And then negative 3 times row 2, so that would be negative 9. And then minus 1. Okay, so this is negative 10, and this is negative 15. Oh, this is going to turn out nice. Okay. All right, what do we want to do next? Oh, it's looking good, isn't it? Look at column 1. Yay, yay. Now we come to column 3. Time to make a pivot right there. Okay, that's not bad. We just need to make a negative 1 a positive 1. Do that, no big deal. Just multiply row 3 by a negative, and that's your new row 3. Okay, very manageable. So we've got 1, 0, 1, negative 3, negative 4, 0, 1, 1, 3, 4. My new row 3 is 0, 1, 1, no, 0, 0. 1, negative 10, negative 15, and then this is not changing just yet. 0, 0, negative 4, negative 10, 15. Okay, so we've got our pivot in place. Use it now to zero out everything else in the column. So use this 1 to make this 1, and this negative 4 is 0. Okay? How would we do that? Well, we would take negative row 3 plus row 1. That would be my new row 1. Same thing for row 2. Negative row 3 plus row 2 is my new row 2. And then lastly, for row 3 plus row 4 is my new row 4. Definitely pause the video here, try it yourself, and then see if you can do it correctly without messing up. If you need to do scratch work, do scratch work, but the goal is to do this mentally, okay? All right, so let's check how you guys did working on your own growing up. So you should have now, I'll do all the new rows in different colors. 1, 0, 0, 7, 11. I missed July 11th this year. I forgot to go get my free Slurpee. I'm sad. Okay. New row 2 should be 0, 1, 0, 13, 19. Row 3 did not change. 0, 0. If you changed it, you did something wrong. And then new row 4 is 0, 0, 0, negative 50, negative 75. Okay, great. Great, great, great. How'd you do? Column 1, column 2, column 3, all looking fabulous. Need to make a pivot right here. Yes. The only way to do it is negative 1/50 times row 4 is the new row 4. Okay, rows 1, 2, and 3 are not changing. And let's rewrite them. 1, 0, 0, 7, 11, 0, 1, 0, 13, 19. 3 is 0, 0, 1, negative 10, negative 15. New row 4. 0, 0, 0, 1, 3 halves, yeah? Good. No decimals, please. Don't be silly. Only use them if the problem introduces decimals. Okay, reduced fractions, always and forever. So here we go. Now we've made the pivot. We're going to use it to zero out everybody else. Great. How are we going to do it? Can you do this part already? You don't need me to tell you what to do, right? So we'll take negative 7 times row 4 plus row 1. That's my new row 1. Negative 13 times row 4 plus row 2. That's my new row 2. And then 10 times row 4 plus row 3 is my new row 3. So everything is going to change except for row 4. Let me list out row 4 then. 0, 0, 0, 1, 3 halves. So we actually already know what x4 is. How exciting for us. Okay, here we go. So negative 7 times row 4 plus row 1. The only entries I'm going to have to pay attention to are in column 4. Everything else is the same, right? So this is going to be 1, 0, 0, 0. And then, oh, I meant the last column here. So negative 7 times 3 halves plus row 1. So negative 7 times 3 halves, that's negative 21 over 2, plus 11 is 22 over 22, so this is going to be 1/2. Okay. Negative 13, row 4 plus row 2, so this stays 0, 1, 0, 0. Okay, negative 13 times 3 over 2, that's negative 39 over 2, plus 19 is 38 over 2, so this is a negative 1/2. And then this is 0, 0, 1, 0. So 10 times 3 halves is going to be 15, plus negative 15 is 0. Okay. Nice. Nice, nice, nice. We're all done. Oh, look it, we survived. Okay, so we've got that x1 is equal to 1/2. x2 is equal to negative 1/2. x3 is equal to 0, and x4 is 3 halves. Okay, so you could list out everything as an ordered I don't know. Do you say quadruple? Like so. Oh my goodness, one unique solution. It's so beautiful, right? I love it. I love it so much. Okay, we've got one more definition and like a little baby proof. How cute. We're going to be doing more proofs throughout the course, so let's just start off nice and easy. Definition. The trace of an n by n matrix. Oh, so notice, same number of rows and columns means it's a square matrix. And the trace is the sum of the main diagonal entries. So that is the trace of A equals A11 plus A22 all the way up to ANN. NN. Nancy. Okay. Prove that if A and B are square matrices of order n, then the trace of A plus B is equal to the trace of A plus the trace of B. All right, so A and B are both square matrices of order n. So that means I could write out matrix A in the following form. It would have A11, A21, all the way up to AN1, right, in that first column. Second column would be A12, A22, all the way up to AN2. And it's a square matrix, so this is going to be A1N, right? Last entry of this row would be A2N, all the way to ANN. Okay. The trace of A, how would you find the trace of A? Remember, it's the sum of the diagonal entries. So these would be the diagonal entries. The trace of A would be A11 plus A22 all the way up to ANN. You just sum up those entries that lie on that diagonal line, okay? And then we also are talking about matrix B. It has the same size. It's also a square matrix, but it's got different entries. So you would say, all right, the entries are B11, B21, up to BN1. Then the next column would be B12, B22, up to BN2. Keep it going, B1N, B2N, BNN, right? Could you find the trace of B for me? Yes, we can, Professor V. Oh, good. Okay, so the trace of B, learn your notation, would be B11 plus B22 all the way up to BNN. Okay? Now what we're trying to show is that the trace of A plus B is equal to the sum of each of these traces separately. Okay, so what would matrix A plus B look like? Because that's also a matrix whose trace I need to find. Remember how we add matrices? Well, I didn't actually do an example with you guys because it's pretty straightforward. So we'll look at it now arbitrarily. So we've got A11 plus B11. When you're summing up two matrices, they have to have the same size. You just add the corresponding entries. So that's the new row 1, column 1 entry. Then just keep going. You would have A21 plus B21 all the way down to AN1 plus BN1. Like that. And then the next column would be A12 plus B12, A22 plus B22, all the way down to AN2 plus BN2. And then the last entry of that row would be A1N plus B1N. Keep going, A2N plus B2N. And then the very bottom, you would have ANN plus BNN. Okay, so that's the matrix A plus B. That's how you would find it. So could you tell me what the trace of this matrix is? The trace of A plus B is the sum of the diagonal entries. Okay, so all of these guys basically. Yeah? Okay, so it would be A11 plus B11 plus A22 plus B22 plus everything up until ANN plus BNN. Okay, well the proof that we're trying to work out is that this trace of a plus b is equal to the trace of a plus the trace of b. So we're just going to use our associative and commutative properties of addition. That's all it boils down to. And you probably learned this when you were a wee thing. Yes? So I can regroup. You can drop all the parentheses and rearrange the terms so that they're in the following form. A11 plus A22 plus you'd have A33 all the way up to ANN plus, and then I'll group it B11 plus B22, everything else up to BNN. And then these terms here are precisely the trace of A, and these terms here are the trace of B. So we showed what was asked of us. Pretty straightforward. Don't worry, the proofs will get more interesting later in the course, but this is just initial exposure if you haven't done any before. Okay? So give the video a thumbs up if you found it helpful. Subscribe if you haven't already. If you are looking for more content, check out the rest of my playlists on my YouTube channel. Also join my Patreon if you want exclusive content on demand for patrons only. All right, stay tuned, guys. Got lots more coming your way.